Welcome grade 12s to STEM in Action's Boost series. I'm V Guyan and today we're going to have a look at the Doppler effect. Some pre-knowledge that you need to know from grade 10 and 11 before we can get started with the Doppler effect. You need to remember your properties of waves. Things like wavelength, amplitude, frequency and period. We also need to know about the properties of sound, pitch, loudness and quality of sound. And then from maths, we need to know about fractions, the effect of the denominator and numerator on the solution for a fraction. So what is the Doppler effect? The Doppler effect is the change in frequency or pitch of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. This is a formal definition that you would have to use in an answer in an exam paper. Let's have a look at a simple demonstration of the Doppler effect. Let's have a look at a simple demonstration using a tuning fork. If I have to tap this tuning fork against something, it then emits a sound of a certain frequency. I can then swing this tuning fork around, changing its velocity relative to you, the listener, and you should then hear a different pitch as the tuning fork is moving, although the tuning fork itself is not changing the sound that it is emitting. Good. All right, so there we had a demonstration of what the Doppler effect sounds like. So before we get into it in more detail, we need to remind ourselves what is frequency. Remember that frequency is the number of waves in a given time. So if we have a look at the police car there in the picture, it is emitting a sound wave, and that sound wave is moving outwards to the people on the left and right hand side. The waves are reaching both of them at the same frequency. They are the same number of waves passing each person in the given time. Also remember that frequency is equal to 1 over period, and period is equal to 1 over frequency, where period is the time taken for one wave. So if we then have a moving observer or source, that is when we're going to get a shift in the pitch that we hear. And so we get the frequency that the listener hears. Right? Remember that frequency and pitch are related. So if we're hearing a different pitch, it means the frequency that we're hearing has changed. And this is known as the Doppler Equation. FL is our observed frequency, our frequency of our listener. V is the speed of waves, the speed of sound, which is normally around 340 meters per second. This will be given to you in an exam question. Vs is the speed of the source, so the object that is emitting the sound. For example, the tuning fork or the police car in the previous picture. And VL is the speed of the listener or the speed of the observer. So, if the source is moving, how does this look in the formula? Well, firstly, if the source is moving, that means our listener is going to be stationary. So already we can eliminate the VL out of our equation. So if we have a look at our equation, we can see over here VL, the velocity of the listener, that will become 0 because the source is moving, which means the listener is stationary. Therefore, our equation changes to this. Furthermore, we can have a look at if the source is moving towards the listener. As the source is emitting the waves, it is moving closer to the previous wave, and so there are more waves in a given time that are reaching the listener. Therefore, that means that the frequency is higher. So if it's moving towards the listener, it means the frequency is going to be higher, and so our velocity of our source is going to get a negative in the equation. So down here, there's no longer plus or minus, we now have minus Vs. That is because if we want a higher frequency, we need to divide by a smaller number to get a bigger answer. So we need to make the number at the bottom of the fraction smaller than the number at the top of the fraction. And that is why we are subtracting Vs. On the other hand, if the source is moving away from the listener, we can see that as the source emits one wave, it moves away from that wave before it emits the next one, making the gap between waves larger and therefore the frequency lower, as there are fewer number of waves that pass the listener in a given time. This means that the frequency is lower. And therefore we're going to make Vs, the velocity of the source, positive. If we have a look at our equation, we can see how that comes about. Remember, if we want a lower frequency, we need to divide by a bigger number at the bottom. And so therefore we need to add the velocity of the source. And that is why this becomes a positive here, so that we can get a lower number when we divide. There you can see the two give side by side, so you can compare. When it is moving towards, the waves are definitely closer together, indicating a higher frequency, where on the right hand side, when the source is moving away from the listener, the waves are further apart, indicating a lower frequency. On the other hand, we can have a look at what happens when the listener is moving. And so if the listener is moving automatically, that means that our source is stationary. If we have a look at our formula, that means over here, velocity of the source is going to become 0, and so our formula changes to just have the velocity at the bottom. If the listener is moving towards the source, we can see he passes more waves in a given time than if he was stationary, because he is going towards the waves as they are coming towards him. And so our frequency is going to be higher. And if the frequency is going to be higher, our VL needs to be positive. On the other hand, if the listener is moving, this means that the source will be stationary. And so the first thing we can see is in our formula, Vs at the bottom, the velocity of the source, that will become 0. And so our equation will first change to just the V at the bottom. And that's the speed of sound. If the listener is moving towards the source, we can see that the listener is passing more waves in a given time as he moves closer and closer to the source. This means that the frequency is higher, and therefore VL should be positive. How do we know that VL should be positive? Let's have a look at the formula. Here's our formula. We want our frequency of our listener to be higher, so we need to be getting a bigger answer. And so therefore we need to add VL in the numerator so that we have a bigger numerator than denominator to get a bigger answer. On the other hand, if the listener is moving away from the source, we can see that it's almost like the waves need to catch up to the listener. And so there are fewer waves passing the listener in a given time, which means there is a lower frequency, and therefore VL will be negative. Let's have a look at the formula to see why VL is negative. If we want to get a lower frequency, that means when we sort this fraction out, we need to get a lower answer, and so we need to subtract VL to make our numerator smaller than our denominator. If we just have a comparison of the listener moving towards and the listener moving away, we can definitely see that the listener moving towards is passing more waves and therefore has a higher frequency than the listener moving away, which has less waves passing it and therefore has a lower frequency. So let's have a look at the Doppler effect with light. We need to first remember that a longer wavelength means that it has a lower frequency. Remember that when we're dealing with light, we also have the formula C equals frequency times lambda. And so if our lambda, our wavelength, is longer, means it's bigger, therefore our frequency needs to be lower because C is a constant. And on the other hand, if we have a shorter wavelength, we need to therefore have a higher frequency. So they go hand in hand. And it's important that you know that relationship in order to be able to answer questions on Doppler effect with light. So we can then figure out that if the source moves towards, remember that when our source moves towards, it results in a higher frequency, and therefore we're going to have a shorter wavelength. And this is then known as being blue shifted. If you have a look at our picture at the bottom, we can see that if it's shifting to a shorter wavelength, it's shifting to the left, and so we call it blue shifted. Whereas if the source moves away, when a source moves away, then it results in a lower frequency, and so we have longer wavelengths, and so the light is red shifted, which is on this end of the spectrum. Astronomers use this fact to determine whether stars are moving away or towards us. Most stars are seen as red shifted, and so the light we see from them is more on the red end of the spectrum. This tells us that they are moving away from Earth, and we can therefore conclude that the universe is expanding. Let's have a look at some application of Doppler effects. We'll first have a look at paper 1 from November 2019, question 6. Let's have a look at the applications of Doppler effect by tackling 2 exam paper questions. First, we'll have a look at question 6 from November 2019, paper 1. Question 6 says, the siren of a police car, which is traveling at a constant speed along a straight horizontal road, emits sound waves at a constant frequency. Detector P is placed inside the police car, and detector Q is placed next to the road at a certain distance away from the car. The 2 detectors record the changes in the air pressure readings caused by the sound waves emitted by the siren as a function of time. The graphs below were obtained from the recorded results. Graph A is for detector P, which is in the car, and graph B is for detector Q, which is next to the road. Question 6.1. Different patterns are shown above for the same sound wave emitted by the siren. What phenomenon is illustrated by the 2 detectors showing the different patterns? So if we have a look at the different patterns, we can see that there is a difference in the time taken for one wave for detector P and for detector Q, which tells us that there is a difference in frequency from the source to the observer, and therefore we can see that it is illustrating the Doppler effect. So question 6.1, the answer is Doppler effect. Question 6.2. It then says the police car is moving away from detector Q. Use the graphs and give a reason why it can be confirmed that the police car is moving away from detector Q. So we've got to use the graphs. So if we have a look at the graphs, we already identified that the period is different, and we know that period and frequency are inversely proportional. So therefore, we can have a look at talking about the period to answer our question. Remember that the question says use the graph, so we're not going to talk about frequency because that is not on the graph. We're going to talk about the period, and we can see that the period for detector Q is longer than the period for detector P. Remember, frequency and period are inversely proportional, so a longer period means a lower frequency. If the detector, the listener, is picking up a lower frequency, it means that the source is moving away, therefore confirming what they have said. So therefore we can say detector Q has a longer period than detector P, which confirms the car is moving away. Let's have a look at question 6.3, which asks us to calculate the frequency of sound waves recorded by detector P. We know from our graphs that we have our period, and we also know that frequency is equal to 1 over period. And so if we're looking at detector P, we look at graph A, and we can see the time for one wave is 17 Remember to always check your units because it's 17 times 10 to the negative 4 seconds. And so we have 1 over 17 times 10 to the negative 4. And we're then going to put that into our calculator. And we've got 1 over 17 times 10 to the negative 4. And that will give us a frequency of 588,24 Hertz. We can then move on to question 6.4, and it says use the information in the graphs to calculate the speed of the police car. Take the speed of sound in air as 340 meters per second. So this is where our Doppler equation is going to come into effect, and we know that from the Doppler equation the frequency of the listener is equal to the velocity plus or minus the velocity of the listener over the velocity of sound plus or minus the velocity of the source. And all of that is multiplied by the frequency of the source. Now, we know that detector Q is placed next to the road, and so the velocity of the listener is 0. The listener, or the detector Q, is not moving, and so this is 0. And so we can find our frequency of our listener. Remember, our listener is the detector that is next to the road, and so we know that this is going to equal 1 over period, like we did in 6.3, but now our period for detector Q, we have a look here, the time for one wave is 18 times 10 to the negative 4. And so our frequency there, let's say 1 over 18 times 10 to the negative 4. And so we get 555,56 Hertz. We can then sub that in here. So we've got 555,56 is equal to the velocity of sound is 340. We said the listener is stationary, so that falls away. Over 340. Now we need to decide if it's plus or minus the velocity of the source. Well, remember, the source is moving away. If it's moving away, we want to get a low, well, we expect to get a lower frequency, and we did. We can even check there we get a lower frequency. How are we going to do that? Well, we need to divide by a bigger number. So we're going to add Vs at the bottom, and then we're going to multiply it by the frequency of the source, which is that one there, 588,24. Let's make a little line there so we can see that that's separate. Now we've got to solve our equation, and so there's going to be a bit of maths happening here. First thing I'm going to do, I want to solve for Vs, so I'm going to take this away, and it's multiplied on this side, so when I take it across it's going to be divided. So we're going to have 555,56 over 588,24, and that is then going to be equal to 340 over 340 plus Vs. When we have just one fraction on each side, then we are able to invert both fractions, and I'm going to do that because I want to solve for Vs, so I want to get that to the top of the fraction. And so I'm going to have 588,24 over 555,56, which is equal to 340 plus Vs over 340. And now we're going to get rid of our denominator here by multiplying on this side. So we get 588,24 over 555,56 times 340, which is equal to 340 plus Vs. I'm going to type this whole thing into the calculator to simplify a bit there. 588.24 over 555.56, and that whole fraction is multiplied by 340, and so we get an answer here of 360, which is equal to 340 plus Vs. And so if we want to get Vs by itself, we're going to say 360 minus 340, so Vs is going to be equal to 20 meters per second. And so there we have the velocity of the police car. And that is the end of question 6 from November 2019. Let's have a look at question 6 from November 2017. Question 6 says, A police car moving at a constant velocity with its siren on passes a stationary listener. The graph below shows the changes in the frequency of the sound of the siren detected by the listener. 6.1 asks us to state the Doppler effect in words. You can find this in your exam guidelines, but it should say something like, the Doppler effect is the change in frequency or pitch of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. 6.2 says write down the frequency of the sound detected by the listener as the police car approaches the listener. So if it's approaching, it's moving towards, and so therefore we should be hearing a higher frequency. And then 6.2.2, it's as it moves away from the listener. When it's moving away, we should hear a lower frequency. So looking at our graphs, our higher frequency that's detected is 170 hertz, and so the answer to 6.2.1 is 170 hertz, and the answer to 6.2.2 is the lower frequency that was detected, which was 130 hertz. Always double check the units there that are given on the graph. And so then 6.3 says calculate the speed of the police car. Take the speed of sound in air to be 340 meters per second. So this is similar to the question we did before. So we're going to use our Doppler equation, which says the frequency of the listener is equal to the velocity of sound plus or minus the velocity of the listener over the velocity of sound plus or minus the velocity of the source, and all of that is multiplied by the frequency of the source. But now we have two unknowns because we don't know the frequency of the source and we also don't know the velocity of the source. So we're going to have to make simultaneous equations. So the first thing we're going to have a look at is we're first going to simplify this a bit, and we're going to say when it's moving towards, we'll have one equation, and then when it's moving away, we will have a second equation. So when it's moving towards, the frequency of the listener is going to equal V. Remember, the listener is stationary, over V, it's moving towards, and so we get a higher frequency, and therefore we need to divide by a smaller number. So we're going to subtract Vs and multiply that by Fs. And when it's moving away, very similarly, velocity of the listener is still 0 over velocity of sound. And now, when it's moving away, we expect to get a lower frequency, so we need to divide by a bigger number. So we're going to add Vs. Okay, so now that we have our two formulas, we can fill in the values that we do know. So when it's moving towards, we said in question 6.2.1 that the frequency that the listener would hear would be 170 hertz. So we can fill that in. The velocity of the sound is 340 over 340 minus Vs. We don't know what the speed of the source is, multiplied by Fs. We also don't know what the frequency of the source is, so that's why we're going to have to get two equations so that we can do simultaneous equations. Over here, when it's moving away, the frequency the listener observes is 130, which equals 340 over 340 plus Vs times Fs. So we need to rearrange one of the equations to make Fs the subject of the formula. And so if I take this equation, I keep Fs by itself, I'm going to take this over, it's multiplied here, so I'm going to divide. So I'm going to have 170 divided by 340 over 340 minus Vs, and that will then equal Fs. My preferred way of doing simultaneous equations is getting both equations in the same format so that we can just make them equal to each other. And so I'm going to do the same thing to this equation. I'm going to say 130 divided by 340 over 340 plus Vs is going to be equal to Fs. And now we've got two equations equal to Fs, so we can make these two equations equal to each other. And so we've got 170 divided by 340 over 340 minus Vs is equal to 130 divided by 340 over 340 plus Vs. And here's where our fractions come into play. We've got to remember all our rules here. Remember, if we divide by a fraction, we can tip and times. And so we're going to say 170 times the inverse of that fraction, so it's 340 and we're going to do the same on the other side. 130 multiplied by, we've got to tip and times, so we're tipping this fraction, so it's 340 plus Vs over 340. And then we got top times top, bottom times bottom. So we bring our calculator in. We've got 170. Now remember, this is in brackets, so it's got to multiply both things at the top there. So it's 170 multiplied by 340. We get quite a large number, 5, 7, 800. And then we've also got to multiply it there, so it's minus 170 Vs. All of that is over 340. On this side, we're going to do the same thing. Again, remember that's in brackets, so we're going to multiply it into both. So it's 130 times 340, and we're going to get 44200 plus 130 times Vs, all of that over 340. Now we can multiply both sides by 340, and therefore we eliminate the denominator, and so our equation is simplified to 57,800 minus 170 Vs is equal to 44,200 plus 130 Vs. And so we're going to get all our Vs's on one side. And so we're going to have it's minus 170 minus 130. Make sure you type that in carefully. So you get minus 300 Vs is equal to, and we've got 44,200 minus, when we take this across, so 44,200 minus 57,800, and so we get minus 13,600, and now we're just going to divide both sides by negative 300 by negative 300, and we're going to get 45,33 meters per second as the velocity of the police car. So that brings us to the end of Doppler effect. I hope to see you for our next chapter.